Welcome to the course on transformers, and this is lecture number 2. And briefly we're going to look at construction of transformer, and then we'll look at the transformer on no load. These two topics we're going to cover in this 1 hour video. Okay, so let's begin with construction of transformer. Already in lecture 1 you had seen the working principle of transformer, and then basically what you require at the minimum is a core and the windings. So this is basically the construction like this. Now, what is important in this is whenever I supply this with a sinusoidal voltage, the flux which is generated here has to go and link onto the secondary coil. So this is the primary winding and this is the secondary winding. It is very important that the flux has to go through the core and link with the other coil. Only then the EMF E2 will be induced in that, and that is what is the working principle of the transformer, that we will have to induce EMF into the other coil through mutual inductions. So, so sometimes the flux will be leaking. So this is called leakage flux. So the flux which leaves this coil may sometimes come out into the air and then simply link with only this coil. So if I denote this as flux 1 2, that is flux of one, flux generated by 1 going to link with 2, and here it's only flux 1 which is leakage here. So this is what we need to avoid it. So how can we avoid it? So we can avoid it by placing the coils like this. So let's say physically, so this is my first winding, half of it I'll keep it here and then half of it I'll keep it here, such that uh, the other half I'll keep it like this and then like this. So these two windings, and then here is this and this winding. So out of these two cases, here the scope of leakage flux is less because they are very close to each other, half part is very close to each other. So then there is the scope of leakage flux is less. In fact, the scope of leakage flux is even lesser if I do something like this. I take the first winding and then I just wind it like this entirely. This is the first winding. So let's call it capital A, capital B. And I take another winding and then I'll again wind it on this. So this is small a, small b. So this is primary winding and this is the secondary winding. Here the leakage flux is even more minimum, and this is actually better compared to this one. So this drawing we use only for understanding the concept and working principle of the transformer. But practically when you go to the actual transformer, both the high voltage and low voltage, or both the primary and secondary windings, are actually wound on top of each other in the form of layering. Now you can get a basic doubt. If I do like this, won't it result in a current flow from one coil to the other coil directly? So of course, we'll take care that there is sufficient insulation between these two. Electrically, they are not connected with each other, but physically they are separated by some insulating material. So you can use some kind of a coated wire where two wires, although they are touching each other, there actually no electrical current is passing between them, because there is some kind of maybe some kind of a mica sheet or some kind of a paper is uh, worn inside, so that it is not overlapping, it's not touching electrically, but then physically they are located on top of each other. So this kind of thing is better. So just to summarize, actual practical construction of transformer will be that there will be some kind of a transformer tank. Inside the tank there will be a core, and on that core there will be windings. Now, speaking of core, there are actually two types of cores. So two types of transformer construction mainly. So construction wise, you can make it as a core type and shell type, and also one phase and three phase. So typically, the power transmission, power generation, power transfer over long distances, etc., all the time happens through a three phase system. So therefore, the transformer will be of a type of three phase. So there will be three windings, not two windings. In fact, there will be six windings. three windings of one phase and the three winding one primary side and three winding one each for one phase of the three phase of the secondary winding and so on. Whereas in one phase transformer there will be two windings. You can also use three one phase transformers to build a three phase transformer. So that all you can actually work it out yourself. But then what is this core type and shell type? So in a core type of particular transformer, what is the main difference? What is the main construction wise? What is the difference? Is that in core type transformer, the coils encircle the core. The core is at the center, and the coils are around it. So, as I shown before, let me draw that as a cross section of core type. So, if I represent this is the core, and on top of it there will be winding. So let's call it like this. This is low voltage winding. Here also low voltage winding. LV, LV. And these two are connected in series. So this is whole thing is, so this is my low voltage terminals. So what I'm saying is this, since it's a cross section, actually this is a circular coil like this, and this is also a circular coil. But since I have taken a cross section, that won't be visible. So this is the left side of the winding and this is the right side of the winding and so on. On both sides I have the low voltage winding. Now on top of it I'll have the high voltage winding cross section. So this is high voltage, this is high voltage. This is again high voltage, this is high voltage. And together the high voltage, this is connected here and this is connected here, and this is finally coming out as a high voltage terminals. So basically the coils, so the coils are, this is the core and these are the coils. The coils are encircling the core. So that is why it is called a core type. Now in shell type, so there is only one section of coil. So that is, this is high voltage, this is high voltage. This is again the cross section view. Inside that I have the low voltage. Now the core. The core is like this. Like this. Now if I draw the flux, the low voltage winding creates a flux, for example, and that flux separates here, equally divides into two, and some flux goes left side, and then all that flux will come back here like this, and this flux goes this side and then come back like this. So this will ensure that maximum flux linkages are possible through the core. So here the core material is less, here the core material is more, and all these things. So there are some salient features of these two prominent types. So core type is, as you have seen, it is easy to construct because I just have to wind the windings and then I can do that. So in core type, windings encircle core, whereas in shell type, core encircles winding. So here will be relatively poor linkage of flux, or I could say leakage flux is more. Of course, when I say more, it is not like too much leakage flux, but then relate compared to shell type. So leakage flux is less because you can see based on the construction, it is like that. So this is easy to make and repair, whereas this is difficult to make and repair. But the advantage is here this voltage regulation is poor. So voltage regulation means how it is able to maintain the voltage without, when the load current increases, the voltage drop should not make the voltage go very poor. But then that is not the case with this core type relatively, and here voltage regulation is good. and this is costly, and this is less costly or cheap. This is all again comparatively. When I say it, it is all comparatively. Now, of course, the construction of transformer itself is a very big subject, and there are many industries, or hundreds of industries or thousands of industries all over the world. They are manufacturing these transformers, and if you visit any transformer manufacturing company, you will find, they are using various techniques, which of course I cannot cover in this YouTube video. Except I'll mention that there's few videos on YouTube. So for example, these are the two videos. I'll just paste this in the description. You can click them and then look at them. So what is inside a transformer? It shows the inside parts of a transformer, and construction of a three-phase transformer also is another video. And there are again literally tens or hundreds of videos on transformer construction. So I don't want to speak much on that practical industrial subject there. So please explore yourself, go through related videos, see more and more videos on transformer construction. You will get more knowledge than what I am just drawing diagrams here. So almost my diagrams are bad, but you will get very good diagrams. Speaking of diagrams, I was just checking in Wikipedia, so I found this figure. So this is core type single phase. This is essentially what I had drawn before, and this is shell type single phase. Similarly, this is core type three phase transformer structure, and this is the shell type three phase transformer structure. So like this kind of figures, when you look at them pictorially, it gives you a lot of information. So this I found on Wikipedia. So you can search again online and find out construction of transformers. You will find several resources. So I encourage you to search and then find out more about construction of transformer. So that's all I would like to speak about this topic. Whereas the next topic I'd like to speak is transformer on no load. So we'll come to it next. We'll first begin by studying what is considered as an ideal transformer. So the ideal transformer, it has the following characteristics. First is losses are zero, so there are no losses, and that means everywhere the resistance is zero, reactance is zero, leakage is zero, all these things. So no leakage of flux. So it is important that flux coming from the primary winding without leaking should link with the secondary winding completely. So that we are assuming it doesn't happen, and no core losses also. So the winding which is found on the core, because it's a alternating flux, the direction of the flux keep changing, and under that condition there will be some losses in the core in a practical scenario. But then that also we are ignoring. So under these assumptions, we will consider the transformer to be an ideal transformer. And the ideal transformer will, how it works. First, we should understand that, and then based on that, we can study what happens when there are non-idealities introduced in the transformer. So we'll also assume that for the ideal transformer, the primary winding is connected to rated voltage and rated frequency. So rated voltage and frequency for primary winding. So under that conditions, what happens? Core loss anyway is zero. So under that conditions, so let me draw it as a diagram. So if this is the core of the transformer, then we'll have the winding. So this is the primary winding, and this is the secondary winding. And right now this is no load, and then I am connecting a rated voltage to the primary. So under these conditions, strictly speaking, there should not be any current, but here there will be some minute amount of current denoted by I mu. So this is a magnetizing current, and that current is required to set up the basic flux in the core. So so if I so this let's call it as V1. So if I draw it as a vector diagram of an ideal transformer, so I'll get this is so I'm taking the supply voltage V1 as the vertical line. So normally it is customary to draw like this. So usually we take the voltage as reference like this 0 degrees, but then at 90 degrees we are taking the V1 as the reference voltage. Then the magnetizing current will exactly lag the V1 by 90 degrees. So let's call this as I mu. And as a result of this magnetizing current, there will be a flux called phi m. So this is or we'll just call it as phi. So this is I mu and this is phi. So this is like, and as a result of this flux linking with the coils, there will be two EMFs induced. Now you can denote them as small E1 and then large E1. The length of this will be depending on the small E2 and small E1. So these are induced EMFs. Now, but the way we denote is the capital E1, so that it will be exactly opposite to that. So this is called as capital E1, and then whereas E2 will be exactly equal to capital E2. In fact, we are free to choose the direction of E2. See, I can choose anywhere the direction of E2 because this is electrically a separate circuit. So there is complete electrical isolation is there. So this is electrically isolated with this. So I can draw a separate vector diagram for E2, that is the secondary side, and a separate vector diagram for the primary side. But then for saving the space and for comparing between these two, typically E2 is drawn exactly opposite to E1. So therefore this is nothing but capital E1. Now there are many textbooks, sorry, capital E2. There are many textbooks where this distinction is not made, E1 and small E1 and capital E1. But then I thought, this is more better way because it's a matter of notation. So E1 is induced EMF. I cannot do anything about it. It will always lag behind the flux by 90 degrees, and the flux will lag behind the voltage by 90 degrees. So E1, small E2 are definitely in this direction. But then I am free to choose the direction of capital E1 and capital E2, and the way it is chosen is plus minus here, and this is capital E1, and this is plus minus, and this is capital E2. Now, what is the relation between E1 and V1? Actually, E1 V1 will be equal. So I should be showing like this. So irrespective of the number of turns, because if you look at this in the ideal transformer, both will be equal. Whereas E2 length will depend on the ratio of the turns. So this is about ideal transformer. It is on no ideal transformer, that is. Now what happens when I start adding the load here? So the load, as we discussed, whenever there is a current in the secondary, that current will start inducing its own flux, and that flux will reduce the flux in that flux will reduce the flux in the core, which in turn reduces the induced EMF, thereby sending more current, which will again restore the flux to its original value. All that theory we had discussed in lecture 1. So that applies, and that's how it works. Now we can, from the ideal transformer, we go one step forward and discuss about transformer with core losses. So what is transformer with core losses? So if I go back here, you see the flux which is there is a sinusoidal flux. So the flux is alternating. Let's say the clockwise direction of the flux indicates positive. Then the negative cycle, when it comes, the flux will become anti-clockwise, and all the time the magnetization and demagnetization, reverse magnetization, and so on keeps on happening in this core. As a result, at molecular level, the dipoles in this magnetic core are all the time moving, and that creates heating and heat in the particular transformer core. So that is called hysteresis loss. So basically the core losses are of two types. One is hysteresis. Now we cannot do anything about this hysteresis loss except choosing a better material, because hysteresis loss is a function of the material. And if you have a material with different BH curves, so for example, this is so BH curve is something like this. I think this is the flux density, this is the magnetic field intensity. So as I increase the magnetic field intensity, the flux density increases and saturates, then again it comes back and all. So let's say this is for material A. Now material B, so for example, is like this. So this is H and flux density, and this is material B. So don't confuse between these two B's. Now here you see the area is more compared to the area here. So material B will have more hysteresis losses compared to material A. So therefore we should use the material which has the very least amount of hysteresis losses. So what is the so continuing this, what is the ideal material? So ideal material is something which has a BH curve like this. It's like a straight line. That means it will magnetize and again it will demagnetize and reverse magnetize, again demagnetize and so on as a straight line. So this is the ideal material for transformer. So this is H and B. But of course the ideal material is not will not be there. So this will saturate like this, and then there will be some residual magnetism left once it is magnetized and reverse magnetized. So therefore that shape comes into picture. So anyway, so that is a different studies, different subject. So this is about hysteresis losses because of the material. Also, because of the geometry, there will be something called eddy current losses. So what is eddy current losses? The changing flux is linking with the conductor. So this core itself made of material which is iron, for example. Iron can conduct electricity. So there will be some circulating currents flowing in the core itself, and those currents are eddy currents, and they have some they result in some heating. They also have the losses. So both these losses are core losses. Now to represent these core losses, so if I again connect like this, so there will the core is getting heated, so therefore some active power has to be consumed from the supply. So therefore this I mu is not the I mu is the current will not be lagging V1 by exactly 90 degrees. So it will be something less than 90 degrees. So this is transformed with losses, that is core losses. So there is some current called I naught. So this I naught is the no load current. Now this is not exactly 90 degrees, this is angle of phi naught. Now if you take the components of this, so this component is nothing but I mu, because this is maintaining 90 degrees angle, and the other component which is in phase is called IW. So I mu is magnetizing component and IW is working component. Okay, this is magnetizing component of no load current, so of I naught, and this is also working component of I naught. So therefore I naught, vectorially speaking, is nothing but IW plus I mu. So this is IW plus I mu. So if I add these two vectorially, I get I naught. Now what is the input power? So P naught is nothing but V naught I naught cos of phi naught. So this is the core losses. So this is actually power. So this is the unit is in watts, and that power is called the core losses. Now mathematically you can calculate what is the resistance. So how do you get the resistance? So simply if I divide uh, voltage by current, so that is I naught cos phi or IW. So by the way, here also I can write it. So IW is I naught of cos phi naught, and then I mu is I naught of sin phi naught. If I know these two, I can find out that. And cos phi naught is the no load power factor. Now coming here, so if I divide these two, V naught by IW, then the unit will be voltage divided by current. So the unit will be ohms. So R naught ohms. So let's denote it by R naught. So but then if you actually see, this is not the resistance of the coil. So this, if I go back, this coil is there. This coil will have some electrical resistance because it's made up of a copper wire. It will have some electrical resistance. So that resistance also, so let's say the resistance is RC. So let me draw it. So this is my primary winding and I am applying this one. And this primary winding will have electrical resistance. Let's denote it as RC. Now this RC is not R naught. So what is the losses here? So this is nothing but I naught square into RC is the copper losses. Whereas what are the core losses? So core losses are nothing but this one, the V naught IW or I naught cos phi. So this is the core losses. So typically this I naught is 1% of the full load current IFL. So because this full load, it's 1% of it, it is much less. So this copper loss is neglected. It is under no load. So it is neglected. Neglected under no load. So therefore this R naught is not the resistance of this copper wire. It is actually the resistance of, it is mathematically indicating a resistance of that of the core. Anyway, when we come to the equivalent circuit, at the time we will look at it and see where it comes. But for the time being, we will, the more important point is to know the definitions of I naught, IW and IMU. So once again, if you look at the final vector diagram, so the vector diagram is something like this. So this is the supply voltage V1, and this is the working component of current IW. This is the magnetizing component of current I mu, and the vector addition of these two is the no load current I naught, which is 1% of the full load current, and this angle is called phi naught. Cos phi naught is the no load power factor, and then small e1 and then large e2 are anyway like this, and v1 is equal to e1 here. So this is about the vector diagram under transformer with core losses. Alright, so let's work out some example problems on this so that we get better understanding. Okay, so based on what we have learned about transformer with core losses, let us look at some numerical examples and we'll gain better understanding of what it is. So look at this question. You can try to solve this question yourself and later compare your answer with my answer. So for the time being, let's start. So I have a 2000 by 220 volt transformer. So this is a step down transformer, draws no load current of 0.8 amperes and absorbs 380 watts of power. So let's use our notations. So I naught is the notation for no load current and it is 0.8 amperes. Now I don't know what is the angle of this I naught, so with reference to V. So but let's wait on it. And I have P naught, the no load power is 380 watts. And I also know what is V1. So the V1 is 2000 volts. So from this I can immediately calculate the power factor. So if you look at it, so we know that the no load power is nothing but V1 I naught cos of phi naught. So based on this I can find out what is the cos of phi naught. So let's do that. So that is nothing but P naught by V1 into I naught. So I'll use my calculator to do that. So P naught is 380 watts, and then I naught is, how much is it? 0.8 amperes, and then V1 is 2000 volts. So given this information, I can find out the power factor. No load power factor, PF equal to P naught divided by V1 into I naught. So let's see. I think this should be 0. Okay. Sorry for wrong variables. Anyway, so 0.2375 is the power factor. So I have this 0.2375 lagging power factor. I know. So once I know the power factor, so now I can find out the working component of the current. So working component of the current is nothing but I naught cos of phi naught, which is nothing but, so 0.8 into 0.2375. So let's do that. So I naught, so IW is equal to I naught multiplied by PF. So I'm getting 0.19 amperes. So let me make a note of this. 0.19 amperes is my working component of current. Now I can find the magnetizing component of the current. Simply I naught square minus IW square under root. So this is just from the triangle. So if I draw the triangle, it will be, this is I naught, and this horizontal component will become I mu, and then this is IW. So I naught I know, IW I know, so this is 90 degrees. So I'll get it through this. So let's do that. I mu equal to, so SQRT, square root of I naught square minus IW square. So if I do this calculation, I'll get I mu is 0.777. So 0.777 amperes is the I mu. So in fact, that is what is asked in the question. Find the magnetizing and working components of the current and draw the vector diagram. So let's draw the vector diagram. So how does the vector diagram look like? So this is basically reference, but it is considered as vertical. So this is V1, which is 2000 volts. Now, not to the same scale. Of course, the amperes, current and all, we can use a different scale. So I get this current I naught, and this magnitude is 0.8. And then if I take the components of it, so the vertical component and horizontal component. So this component is I mu, this is 0.777 amperes, this is amperes, and then this is IW, which is in phase with the voltage, so that is why it is having some power loss. So this is 0.19 amperes as we have calculated, and this is 90 degrees. But then what is this angle? This angle we are denoting as phi naught. So to know this angle, I can simply do the cos inverse of power factor. So A cos of PF. So this is phi naught. Now this 1.33 is the angle in radians. So let's calculate it in degrees. So multiplied by 180 and divided by pi. So this will convert the angle into degrees. And you see it is less than 90 degrees. It is 76.26 degrees. So this angle, it is 76.26 degrees. So this is with reference to the V. So this is the vector diagram of transformer on no load, but with core losses. So I hope you understood something by looking at this problem. So let's continue and let's look at one more example. So that is example number 8, and we'll try to solve it. Again, you can read the question. You can, at this stage, I think you should be comfortable to solve it yourself, and you can pause the video and try it. And I'm going to also solve this problem right away. Let's now look at this question. So what is given? On the secondary winding being open circuited, the primary winding of a transformer takes 1 ampere at 0.2 power factor lagging. So the given data I naught is equal to 1 ampere, and then cos of phi naught is given to be 0.2. So of course it will be lagging. The voltage ratings are 1800 and 200. So V1 is 1800. Find the magnetizing and working components of the current. Rating of the transformer is 1 MVA. So I think this is straightforward. This is in fact easier than the previous version of the question. So what is asked here? So working component of the current I can directly get by I naught cos of phi naught. So I can just 1 ampere multiplied by 0.2. So that is nothing but 0.2 amperes of working component current. And then the magnetizing component will be square root of I naught square minus IW square. So that will be, so square root of 1 square is 1, and 0.2 square. So I'm getting 0.9798 as my current. 0.9798 amperes of magnetizing current I am getting. Good. What else? So I think we have calculated both working component and all. Since anyway, even though it is not asked, let's calculate the core losses. Core loss, or in another name is iron loss. Let's calculate the iron loss of the transformer. So what is it? So that is nothing but V1. So this is P naught, V1 I naught cos of phi naught. So I have 1800 multiplied by 1 ampere multiplied by 0.2. So this 18 into 2 is 36, and 360 watts I will be getting. So this is the no load copper loss of the, iron loss of the transformer. So, but the question is, what is the core loss? In fact, yeah, this is actually asked. Core loss of transformer under no load. So this I have calculated. So under no load, the core loss is, we got 360 watts. Now what about half full load? Now you look at this, while the load is changing, what will happen to the core loss? So core loss is completely because of the heating of the core. So core loss is because heating of the core. And heating of the core is because of two things. One is hysteresis effect, and other is eddy current effect. Now look at this hysteresis. Hysteresis, anyway, it is because of the material and the changing flux. So that is nothing but changes in flux. Similarly, eddy currents also, because of the change in flux interacting with the core material, eddy currents are induced, and those currents are circulating in the core material. And by the way, I forgot to mention how to reduce the eddy current losses. So eddy current losses can be reduced by laminating the core. Reduces eddy current losses. So by laminating the core, so what is the meaning of laminating the core? It's like instead of having one block core like this, so one entire block of core like this, you actually have a different stampings, and then each stamping you can stack to each other. So that will reduce the, and between the stampings there is a isolation, electrical isolation. So that will increase the resistance and reduce the eddy currents, thereby reducing the losses. If you still do not understand what is lamination, I just suggest simply go to any browser and search for laminated core of a transformer. Just search for the Google images and you will get the picture what it is literally. Okay, coming back to this, whether it is hysteresis loss or eddy current loss ultimately causes heating and ultimately causes core loss. All is because of the flux, but flux is constant. I mean, what I mean is flux is changing, but then the magnitude of the flux, the magnitude of the flux, that is the RMS value of the flux, does not change with the load. So we have seen that in the earlier lecture, that is lecture 1, as the load increases, the flux momentarily will reduce, but then again it is restored to the old value, that is the initial value. So flux does not change. So since the flux does not change, the hysteresis eddy currents does not change, and in the heating does not change, and therefore the core loss does not change. So therefore whatever value we calculate, 360 watts, so at no load the core loss is 360 watts, at half full load the core loss is 360 watts, and at full load also the core loss is 360. So this question is asked just to confuse you. Irrespective of the amount of the loading, the loss is always same, 360. Then what changes? The copper loss changes. Of course, the copper loss, that is lost because of the current flowing in the windings, which we have not yet considered in this two lectures, but later we will consider that. The copper loss keeps on increasing as we go forward, but the core loss remains constant. I think that's it with this question. So let's go to the next question and we'll try to solve it again. So again, you can have a look at this question. You can pause for a while. You can attempt to answer yourself, and then you can always compare your answer with my answer. So let's start working on this right now. No load current of a 500 kVA transformer is 4 amperes at 0.25 power factor lag. So I naught is 4 amperes, and then cos of phi naught is 0.25 lag when supplied at 230 volts. So V1 is 230 volts, 50 hertz. So F is 50 hertz. I don't know whether this data will be useful or not. The primary has 200 turns. Oh, I think looks like the data is going to be useful. So N1 is 200 turns. The primary has 200 turns. Calculate the maximum flux in the core. So phi max we have to calculate. Alright, so to calculate the maximum flux in the core, we'll use the EMF equation of the transformer. So what is the EMF equation? So V1 or E1 is nothing but 4.44 into frequency into maximum flux into number of windings. So this is in number of turns in the winding. So from this, V1 is given, F is given, N1 is given. So I can find out the maximum flux. So V1 is 230 divided by 4.44. So this is the EMF equation we have derived in the previous lecture. So or the earlier lecture than that. Frequency is 50 and N1 is 200 turns. So let's see how much is it. So 230 divided by 4.44 multiplied by 50 multiplied by 200. So 0.00518, or I can write it in milliwebers, that is 5.18 milliwebers. 5.18 milliwebers. Again, should be careful with the units. All engineers should be careful with the units wherever you go. That's it. I have done this. This is a maximum flux. So what is the RMS value of the flux? So just for the fun. So RMS flux is nothing but maximum flux divided by square root of 2. So that is, let's do it, 5.18 divided by square root of 2. So 3.6628. 3.66 milliwebers. So this is the RMS value of the flux. Although it is not asked, I just calculated. Now, what is the core losses at 75% of the full load? So again, this 75% of the full load is just for to confuse you. Core losses are core losses, whatever is the amount of load. So let's calculate the core losses. So how do we calculate the core losses from the given data? Very straightforward. P naught is nothing but core losses, which is nothing but V1 I naught cos of phi naught. So that is nothing but 230 multiplied by 4 amperes multiplied by 0.25. Now you see 4 into 0.25 is 1/4. So these two will cancel. So I get 230 watts. No need to use calculator on that. Alright, so I calculated this current also. And then magnetizing current. So we had done this before. So how do we calculate magnetizing current? So I knew, first I'll calculate the working component of the current, IW. So it is nothing but I naught into cos of phi naught. So that is nothing but 4 into 0.25. So that is nothing but 1 ampere. And I mu is nothing but I naught square minus IW square under root. So how much do we get in this? So square root of 4 square minus 1 square. Square root of 16 minus 1. Square root of 15. So square root of 15, 3.873. So just for fun, let's also find something like this. Let's find what is phi naught. So what is phi naught? Is nothing but cos inverse of 0.25. Then let's do that. A cos of 0.25. So 1.3181 radians. So phi naught is 1.3181 radians. So the radians can be converted to degrees just for our understanding. So 180 divided by pi. So it is 75.5 degrees. So always this is cross check. This will be less than 90 degrees. So if it is completely 90 degrees, then there is no working component of the current. Now, what is sine of phi naught? Because I know I mu also is equal to I naught into sine of phi naught. So it's a sine component, isn't it? So let's calculate this way. So I get 4 is I naught current multiplied by sine of 1.3181. So let's see how much we get for this. 4 multiplied by sine of 1.3181. So since sine function anyway takes input of in radians, so I can just do it like directly. So 3.873. So 3.873 amperes. This is exactly the same current that we got earlier. So it's another alternative way of calculating it. So I think that's it with this problem. We have solved everything that has been asked. Just again for clarity's sake, let's draw the vector diagram. So how does the vector diagram look like? So this is V1 and the magnitude of V1 is 230 volts, which is also E1. Then I am getting I mu, which is 3.873 amperes, and this is exactly 90 degrees from that of V1. Then I'll get IW. So IW is the working component of the current. This is 1 ampere. This is exactly in phase with this current. And then we have this vector addition, and then I get the current like this. This is I naught, and this I naught value is 4 amperes, and this angle phi naught we had calculated just now, that is 75.5 degrees. So this is the vector diagram of the transformer on no load with core losses. I hope you understood something from this entire lecture. So this is lecture 2. If I summarize this lecture, we had briefly looked at the construction of this transformer, and then shell type transformer and core type transformer. And then I also advise you to look at some other alternate videos, how a transformer is actually manufactured. So there are a lot of YouTube videos where you get the factory, and in the factory people are building a transformer. You can all see the process how it is done. So just like robots building cars, we have uh, either robots or people building transformers. So you can have a look at that to understand the construction. And then we looked at the case, ideal transformer case, and transformer with losses. So and we have solved some of the problems. So with this, I'll end this video, and we'll see in future videos. Thank you.